Good morning. My clock here just clicked to 9 o'clock, so we're going to go ahead and get started. My name is Mike DeLaCluse. I'm president of the Lesman Instrument Company. I'd like to thank all of you for taking time out of your busy schedules to join us for Introduction to Air-Fuel Ratio Control by Lesman's own combustion specialist, A.J. Piskor. Today, A.J. will help you understand why it's important to check and reset your air-fuel ratio control to maximize efficiency in process heaters, furnaces, ovens, boilers, just to mention a few. It's really the basis of combustion, so we should have called this webinar Combustion 101. AJ joined Lesman earlier this year as our combustion and control specialist after spending 10 years with our manufacturer partner Maxon, now a Honeywell company, as a sales engineer. He's also a huge Green Bay Packers fan who forgot to wear his lucky socks yesterday, so he's thrilled that they won last night. We will be muting the phone lines. There is a question tool built into GoToWebinar. If you have a question, feel free to type it in. I'll be monitoring that. We'll also have a question session at the end, so feel free to jump in at the end. With that, I'm going to turn it over to AJ.
All right, thanks for the introduction, Mike, and thank you, everybody, for attending. I'll go through here just a quick overview of this webinar as well as a preview for the upcoming webinar that we will do next month. So today, in the Intro to Air-Fuel Ratio Controls, we'll first go over a combustion terminology and fundamentals. Again, this is a intro course, and it's important, I think, that we just cover some of the basics of combustion so that once we start talking about the importance of air-fuel ratio, we're all using the same terminology. I'll also go over the importance of air-fuel ratio control, how this affects each and every combustion process, and then I'll step through and go through the methods of air-fuel ratio control and the pros and cons of each method, as well as the critical component in each of those methods. Next month, I will cover a more advanced air-to-fuel ratio control webinar. This will be a good benefit for maintenance personnel and people that get their hands on this air-fuel ratio control equipment. Some to-dos and definitely a lot of not-to-dos when it comes to maintaining and adjusting these air-fuel ratio control products. I'll also go through some best practices and techniques from my time at Maxon, specifically with their products, and also go through and do some sample calculations, just showing you how some simple adjustments could save you some considerable fuel costs over the span of the burners. So we'll get into first just a couple of common combustion terms that I want to just reiterate. Combustion, of course, defined as the rapid oxidation of a fuel, usually via the oxygen present in air, resulting in the release of energy, heat, and light. I like to refer to combustion as the controlled oxidation, and explosion would be the uncontrolled. Of course, we're here all for combustion and control, specifically controlling that air-fuel ratio. There's also different ratio terms. So stoichiometric ratio is the perfect amount of oxygen and fuel that is theoretical. It's obviously we're not in we're in the real world, so this is fairly rarely the case that this equation holds true. But from a combustion standpoint, we like to refer to stoichiometric as the baseline, and then when we set up our burners, we adjust them to be either with excess air or excess fuel, which I'll cover in the next slide here. So here's an example reaction showing natural gas as the fuel. We show 2 parts oxygen, 8 parts nitrogen. Of course, that's the constitutes of air, which have 8% nitrogen, 20% oxygen. So in this equation, if we want to simplify, we can say just 10 parts of air for every part of natural gas. That would, and then your byproducts on the right side of the equation would be your carbon dioxide, water, and then the nitrogen that's going along for the ride, plus, of course, your heat. When we start introducing additional air into the equation, a lot of times we'll refer to this as excess air or lean combustion. So most industrial process heater applications run with excess air. This is in an effort to ensure that there is no wasted fuel, as well as maintain a lower temperature of the flame and shape the flame to a desired shape, or affect the velocity of that flame exiting the burner. So an example here, we're showing a natural gas burner that's receiving 15 parts of air for every part of fuel. So the first 10 parts, as I hit on before, is the stoichiometric ratio. That's the exact amount of air needed to convert that fuel. We have 5 additional parts of air that are going along for the ride, and that air is considered our excess air. So we can describe this burner as running lean, and we can take a look at the sample equation below, showing that we have oxygen and 12 parts nitrogen now on the right side of the equation. The opposite of excess air would be excess fuel. This can sometimes be described as a rich running flame or rich combustion. So this is when actually less air is present than necessary to combust the fuel. And by present, I mean being introduced into the burner itself. All the fuel eventually is combusted, but what happens with excess fuel applications is they may want to, instead of forcing all the combustion air through the burner, they may want to have the flame and the fuel react with the chamber that it's firing into and use the oxygen that's available inside that chamber. So that's a desired effect, especially for processes where you're doing some kind of metal coating that has a rapid oxidation, or you're putting on, or it's highly corrosive. You do not want that oxygen to interact with the product. You would run your burners with excess fuel or run them rich to control that reaction from occurring on your process. So we look at the equation below, and we have 2 parts of natural gas for 10 parts of air, and we see that we have the extra natural gas, the CH4, on the right side of the equation in this example. So the cornerstone of combustion, I think we've all heard of the triangle, the flammability triangle, the combustion triangle. You need to have air, fuel, and an ignition source. But one common mistake with that generalization is that you need to have the air and the fuel in the right proportion to each other. So all fuels have a lower and upper flammability limit. So when we look at mixing air and running burners rich or lean, you still have to be within your lower and upper flammability limit. Otherwise, you will not be getting combustion, even with the ignition source. So combustion can only occur between the lower and upper flammability limit. And what we're going to dive into, and a key part to maintaining good control of your oven or furnace or dryer, is that when you change the firing rate of a burner, both the air and the fuel need to travel together so that you stay within the limits of flammability. So I list out 3 common hydrocarbon fuels that are used in combustion, showing the lower flammability limit, upper flammability limit, and then what the stoichiometric ratio would be for that fuel. So for natural gas, we can do essentially 5% of fuel in the air-fuel mixture, all the way up to 15%. The stoichiometric example that I provided, where we have 10 parts of air for every part of fuel, would be about a 9.1% mix. And then we list propane and butane underneath that. We see that both of those lower flammability and upper flammability limits, as well as the stoichiometric percentages, go down due to the calorific value that is in each of those fuels. So propane has a calorific value of about 2,500 BTUs per cubic foot. Butane is going to be about 3,200 to 3,300 BTUs per cubic foot compared to natural gas. which is only about 1,000 BTUs per cubic foot. So that's it for the fundamentals that I wanted to touch base on before we start getting into the air-fuel ratio control. So why is air-fuel ratio control important? Well, obviously, as I stated before, you need to be within your limits of flammability. The majority of combustion processes, ovens, furnaces, dryers, in an effort to maintain temperature will increase, decrease firing rate. There are some other applications that are either on-off or high-low. They also utilize air-fuel ratio in their own ways, but for today's purposes, I'm going to talk a little bit more about dynamic systems where we're controlling and throttling the firing rate up and down and how the air-fuel ratio control maintains that ratio during the separate firing rates. When you have optimal air-fuel ratio, this can prevent nuisance shutdowns. And as I stated before, when you have that flammability limit, that upper and lower flammability limit, if you at any point during operation or during travel from and changing between firing rates, if you go outside of that lower upper flammability limit in that envelope, you could have a shutdown condition. So this will essentially, the flame safeguard monitoring the process will lose the flame signal as it goes out after you lose combustion, of course, causing you to shut your process down and having to repurge your system and relight off and potentially scrap any bad product that might have been in your furnace at that time. Having an optimal air-fuel ratio can also improve your fuel efficiency. So when you have a burner system that's designed and set up specifically to maintain a certain air-fuel ratio, whether that's excess air, excess fuel, or stoichiometric, that burner and the flame shape and geometry in that application is designed to give you certain velocity, mixing energy into your system, as well as temperature. If your air-fuel ratio control goes one way or the other, it could still stay within the limits of flammability, but if it's running a little too rich or too lean for its design purpose, you could use additional fuel to either maintain temperature in the chamber or the temperature that you're trying to impart on your product. So having optimal air-fuel ratio will help significantly with your fuel efficiency. It can also help you obtain tighter control for emissions-driven applications. When you've got a low NOx or low CO burner or application, and I'm referring to simply a direct-fired application, not talking about flue gas recirculation or ammonia scrubbers or anything like that. If we're looking to try to maintain a good NOx or CO production with a direct-fired burner, the burners are designed to have the optimal emissions at a very narrow window within that limit of flammability. So my time at Maxon, we did a lot of work with low NOx burners, and they typically ran with excess air, somewhere in the 30 to 50% region. You can run the burners at a lower percentage of excess air, and you would be able to maintain temperature, and you've got reliable flame signal communicating back to your panel. But once you start going down in your down to below 30% excess air, you'll start to see your NOx production increase. So if you've got the optimal air-fuel ratio control that is repeatable and reliable, you can ensure that you'll stay within that optimal window to maintain good NOx or CO production, depending upon what's most critical for your application. Optimal air-fuel ratio can also help obtain better temperature control. So when we look at just maintaining a temperature, certain methods of air-fuel ratio control provide better resolution, meaning that a small increment in temperature control signal will actually physically move the valves, allowing it to react and adjust properly and maintain a tighter control. Some other systems or control valves that take a large step change to make a big jump to physically move the valves will require, what we'll see there is we'll see a larger temperature fluctuation in the process. And sometimes it's not as critical, but for other applications where compliance is an issue and extremely sensitive, having the proper air-fuel ratio control makes all the difference. So now that I've iterated the importance of air-fuel ratio control, I want to go over the different methods of control and touch base on those a little bit. And I'm going to start with what I view as the most simplistic method and then work my way to the more complex advanced methods of air-fuel ratio control. So the first method that we are looking at are inspirators. So an inspirator essentially uses a high pressure of fuel that's delivered to the inlet of the inspirator, and then there's a Venturi tube design that will pull in combustion air around the high pressure fuel. And this will ultimately give you a ratio of air to fuel. So this method, although in most of the combustion world it's seen as strictly a mixing device, it is a ratio control device as well, since the design of the fuel nozzle and an air adjustment damper will affect the ratio within the burner. And the diagram here shows a cutaway view of a Venturi tube, and we see that the cloud of gas that is jetted in at a high velocity slows down as the primary air is inspirated around it. So inspirators have approximately a 4-to-1 turn down, and I think that's on a pretty good day. So the pros of inspirators, that they are a very low-cost, simple design. It's a scalable technology, so it can go through and you can use it in smaller applications down under 100,000 BTUs or into tens of thousands of BTUs. And they also are available in much larger sizes as well. The cons are low turn down. Actually, available in smaller sizes should be one of the pros, and I have it listed there. But the main con with the inspirators are the lower turn down. So if we're looking to try to get increased control out of your system or being able to control over a wide range, the inspirators aren't really the best at providing that flexibility. In the inspirators, the critical component would be the gas nozzle or the spud. In my opinion, you could also make an argument for that air damper on the back. That gas nozzle has an orifice that's drilled specifically for that capacity and that application. The ratio, essentially, you get the turn down by adjusting the gas pressure into the inspirator. There is no dynamic airflow adjustment. You have that shutter, which is fixed. So you put that in a position. You may fix that at a high fire condition, and then you turn that gas down as low as it can go to maintain the flame on the burner end of the inspirator. So again, it's a good. We see this a lot in applications where they want to spread heat out, and the good thing about these is that since they're low cost, you can do multiple inspirators, and then to get your temperature control, you can turn them on and off as needed. The next method of air-fuel ratio control are cross-connected ratio regulators. These are going to be a lot more common in the combustion world. So there's a couple of different components that would make up a cross-connected ratio regulator. We have an air control device, which is the first component. This can be either done with a control valve, so either like an air butterfly valve or air damper with a control motor that would throttle your air up and down. We also then have, on the fuel line, we would have our Proportionator or our Ratio Regulator, as well as the limiting orifice. So in this scenario, the control signal is sent to that air control device. So whether it's the variable frequency drive on your combustion air fan or to the control motor on the air damper control valve. The temperature control signal is sent there. The impulse line is going to be installed downstream of this device, and that impulse line will send a signal. It'll feed essentially air pressure into the top part of that ratio regulator. So as that ratio regulator sees an increase or decrease in air pressure from the air line, it will then increase or decrease the amount of fuel that it allows to pass through. The limiting orifice, which is downstream, is a fixed device, and what you would do when setting these up is that you would typically throttle your air up to high fire, and then that limiting orifice, you would open or close that and fix that so that you get the proper air-fuel ratio at the high fire set point. These regulators will give you a lot more turn down than the previous inspirators. We're looking at approximately 20 to 1 turn down. The pros on these is that it's a flexible installation, and it's also a relatively low cost. It'll be more expensive, of course, than the inspirator. There's a couple more components there, but it's going to give you better turn down and control than the inspirator. The flexible installation in that you can have your air line and your fuel line separated from each other, and then it would just be a question of how long your impulse line is run. You want to try to keep that as short as possible, but you can go through and have the air line and the fuel line physically separated and connected with your impulse line. So you've got different locations to put these in and install these in. The downside of the ratio regulators is that there is minimal characterization. I think there is an adjustment point on most of the ratio regulators, and of course you have your limiting orifice. So essentially you have 2 points of adjustment. So typically, like I mentioned before, you would set up the limiting orifice to just high fire, and then you would, if the adjustment is available on the ratio regulator itself, you would use that to set in or dial in your low fire or essentially the proportion of the air to the fuel. Again, the critical component here is the impulse line, right? If we think about if anything were to happen to that impulse line, or if there's any kind of moisture or debris that would get in there that would affect the changes in pressure, that would be a huge headache from a maintenance standpoint and maintaining your air-fuel ratio control on the system. So impulse line here is critical for these to operate smoothly and effectively. The next method that I'll talk about is the mechanically linked control valves. I'm sure we've all seen these where we have a air valve and a fuel valve that are connected via mechanical linkage. A lot of times we'll see these in boiler applications as a jack shaft. They also will a lot of times have characterizable fuel valves that will offer adjustment capabilities over the entire range of operations. So if we go back to ratio regulators for a minute, the way that those are set up is that you've got your air valve moving up and down, and your gas is essentially fixed to the air valve. But if you wanted to tweak and make micro adjustments along the stroke between low fire and high fire, you don't have that capability with a ratio regulator unless you start adding additional components into the system. With the mechanically linked valves, a lot of them have a screw carrier assembly at different index points between low fire and high fire. So this will allow you, to a certain degree of flexibility, give you a unique curve between low fire and high fire. Due to the method of mechanical linkage, it's not just limited to just your air and your fuel. You can do this with multi-fuel applications, and you also have the ability to do this with an oil-fired application as well. Next page here shows a picture of this is a triplex micro-ratio valve arrangement by Maxon. So it shows the oil valve on top with the gas valve in the middle and the air valve on the bottom. The two large assemblies to the left next to the oil and the gas valve are that screw carrier assembly. So within there, there'll be 12 screws that you can adjust the shape of the, essentially the profile of the oil or the gas flow on each of those devices. Mechanical linked valves will offer you a little bit more turn down. You can see up to 40 to 1 with this design. Again, that's under optimal conditions with properly sized components. Gas regulators on your fuel train, oil regulators, as well as what the burner can handle. So a good pro here is the high turn down. This will give you good flexibility for your process. It gives you more characterization. Cons on this one would be that once you start adding more and more control valves and longer jack shafts, you'll have higher torque requirements for your control motor, so you may have to size those up to accommodate your torque requirements. And then I put on here less flexible installation. If we look at the picture of the control valve assembly that we see here, we have our air valve right on top of our gas valve, which means that when we lay out or design our system, our air manifold and our gas manifold have to run parallel to each other and within a few inches of each other, at least at that portion of your system. So when you look at using these mechanically linked valves, you have to start planning and designing where your fuel train goes, where your combustion air blower goes, so that at some point between the gas train blower and the burner assembly, you have these lines all close enough to each other to be able to utilize mechanically linked valves. And the critical component here would be the linkage arm between the air and the fuel valve. Obviously, if you with linkage, you put and set those toggles and you screw them in tight enough, and everything works good. But in a real world, linkage can come undone and unhooked. And if we lose the linkage between the control motor and the valve assembly, it's not such a big deal. It's still maintaining ratio, but now we're not getting temperature control. It is an issue nonetheless. But if we do lose that linkage arm between the air and the fuel valves, and we look at the way that this linkage is arranged, actually where the knob is next to the oil valve is typically where the control valve would connect to. So if we lose that connection, we could, in theory, start opening up our fuel without introducing that air, causing a unsafe condition rather quickly. So that's a big downside and something that maintenance guys need to be on the lookout for and making sure that it's a good, solid connection there. Okay. All right, so moving on, we're starting to make a jump in the combustion technology. This is fairly new technology within the last 15 to 20 years. We're starting to undo the mechanical linkage and go with electronically linked control valves. So sometimes we refer to this as parallel positioning. So what this system looks like is that there's a central control interface. It would receive your control signal from the temperature controller, and then based on a set of parameters that the burner technician would install or essentially adjust, it would communicate and translate that control signal out to multiple actuators. So there's certain products that can control up to 4, and I think there's even some other ones that can control up to 8 or 10 actuators with one control signal. With this electronic linkage, these systems need to make sure that the actuators are traveling together, right? The ratio regulators with the impulse line, the mechanically linked control valves with the linkage arms, ensure that that the air and the fuel travel together. But with electronically linked valves, there's no physical connection between them except for the wiring. So there needs to be feedback back to the control interface to let them know that the air valves and the fuel valves are in the right position and are traveling together. So we've got built-in safeties to ensure that that happens and maintains the ratio. All the actuators in most of the parallel positioning products are fully characterizable, right? So in the previous example that I showed, let me actually just jump back here. On the mechanical linked valves, the way that these are typically set up is that you set your air valve at low fire and high fire by adjusting the linkage arm between the air and the gas valve. So you have 2 points of characterization there on the air, but then as you adjust your gas up and down, you have all those screw carriers, or you have those screws within your screw carrier assembly that allows you your fine tuning and your fine adjustments there. But your air valve in this example, you really only have 2 points of adjustment. Moving forward with the electronically linked control valves, you now have full characterization over that air valve, so that you're not just setting low fire and high fire and doing a linear ramp between the two. If the application calls for it and you want to get additional characterization out of your air valve, these electronically linked control valve products will give you that characterization. We see this type of system commonly used in emissions-driven applications because of the repeatability of control and the amount of characterization. As I had previously touched on, it's important that we maintain very, very tight control for an emissions-driven application because not the flammability, but that optimal NOx window is so tight, and these emissions-driven applications have permits associated with them, so being outside of that permitted allowance for NOx and CO could levy fines and could have some other undue circumstances on the process itself. So having a system that gives you the tightest of ratio control will give you and the customers peace of mind to know that they've got the right application or the right control system for that application. You can maintain tight ratio control with the previous mentioned mechanically linked control valves, but there is a little bit of slop or hysteresis. As the valves move up and down, they may stray apart from each other, and with extremely sensitive emissions-driven applications, even the smallest hysteresis could cause a system to go from being in compliance to not being in compliance. This also gives you a good amount of flexibility. Since the air valves and the fuel valves do not need to be located next to each other, it's just wiring between them. You can go through and install these wherever you want. You don't have to go through and make sure that your combustion air blower and your pipe train are going to be parallel to each other when you are installing these. These will also give you about the 40 to 1 turn down with the caveat of everything else in your system is sized up appropriately. Again, hitting on the pros, it's got it allows you for flexible installation and gives you great resolution as far as getting tight temperature control and repeatability. The cons is that now we've got additional electrical components that we're adding into our control system, so there's some complexity there. You would have to add interlocks into your control panel to ensure that everything is okay from the air-fuel ratio standpoint, which we didn't have before. And then there is some associated costs, of course, with the additional components. The previous mechanical linkage would have 1 actuator. These systems would have a minimum of 2 and then up to 4, 6, and beyond. The critical component here would be the control interface, of course. This is the device that would store what we call the valve curves, essentially what each actuator will travel to depending upon the firing rate demand going into that control interface. So if that's not set up properly or not working properly, then your system's at a standstill or in an unsafe condition. The last method that I'll cover would be the fully metered mass flow control. And this one will utilize air and fuel flow meters to get flow feedback into the system, and that flow feedback is used in conjunction with your electronically linked control valve. So instead of the previous example where my control signal comes in and it takes that control signal, let's say 50% firing rate, it says, okay, air valve, I need to go to 45 degrees open. My fuel valve, I need to go to 30 degrees open. What the fully metered mass flow control will do is it will take not only that 50% firing rate input, but it'll say, okay, 50% firing rate, my air flow needs to be at 10,000 SCFH, and my fuel flow needs to be at 1,000 SCFH. And then it will adjust the valve position to make sure that it's maintaining that mass flow rate. So depending upon your chamber conditions or any other outside influences, that may be 45 degrees, 48 degrees, 47.2 degrees. It'll continue to adjust and maintain the flow and not just stay at that current valve position. So it's always looking at flow feedback and maintaining the flow as opposed to maintaining position. So again, this is also used in emissions-driven applications. And these would be emissions-driven applications where not only do we need to maintain a low NOx or CO level, but we also have an application that is rather unpredictable. The chamber pressure will fluctuate as different process conditions come up. And so the air-fuel ratio control system needs to see those and be able to respond to those to maintain the low NOx or low CO requirements for that system. And again, just like our parallel positioning, these are also flexible to install since the air and fuel valves and the flow meters are all electronically linked. They don't physically need to be located by each other. This one has maybe about a 20-to-1 turn down. I step it back, even though it's using similar or the same air valves and fuel valves. The resolution of those airflow controllers and fuel flow controllers or flow bodies are limited. They may not be able to give you the reliable 40-to-1 or measurements over the entire 40-to-1 turn down range of the previous example. So I'll scale that back to 20-to-1. Still a very good number as far as getting flexibility out of your process. Pros here, of course, it's going to give you the best available control technology. Some applications or some requirements will call out best available control technology, and it's up to the manufacturer of the equipment to dictate what they deem as the best available control technology. The example here is another Maxon product. It's their Smart Fire system, and this one, as you can see on this block diagram, it takes a firing rate in from a process controller. It goes into an interface panel, which then communicates to the air valves and fuel valves and air flow controller and fuel flow controllers. It'll get that feedback and make those adjustments to maintain those flow rates, and it also communicates with your burner management system and provides feedback back to your process controller. With all these components and flexibility, of course, the con is that it's going to be a more expensive solution. And it's also slower to respond to aggressive control signals. So if you've got a system that is at low fire and you want to bring it up to temperature and go to high fire, it may take longer for a system like this to get up to that high fire position just because there's a lot more going on here. There's more communication that we need to see what the flows are before we move our actuators. So it can take a little bit more time to get up to temperature or to respond to different, if you've got aggressive temperature changes. So typically with customers that use this type of system, they will change the, they will adjust their process controller to account for the slower response of this type of system. And again, with same as the electronically linked system, the critical component here would be the interface panel. So everything here that goes through and manages the positions and sees the flow feedback.
We do have a question. Maybe I misread it earlier. Why is parallel position and jack shaft control capable of 40-to-1 and fully metered only capable of 20?
Okay. So the turn downs, and I should maybe preface this before, they're more towards the high end of the capabilities. And it depends upon the application, of course, if all the other associated components are sized up properly. Right? If your main gas regulator is only capable of 20-to-1, well, that will bring your whole system down to 20-to-1. The fully metered mass flow control, on average, what I've seen is about 20-to-1, and it's, again, a combination of the components that are used and the technology being used. If there's a system available that will allow you to get 40-to-1 turn down, out of the flow bodies and the controllers, then there's no reason why you could not achieve 40-to-1 out of the fully metered mass flow control. Any other questions?
No, you're being conservative.
Okay. Well, so actually that wraps up my presentation. So again, thank you guys for attending. I encourage you guys to contact me with any additional questions that you may come up with after this presentation is done. If you have any other topics that you would like me to cover in the advanced class, please let me know. Again, in the advanced class in January, I'll go over some additional calculations. So I'll show a sample calculation of, for instance, right now it's starting to get colder outside. Some applications that are pulling in cold air from the outside and bringing it into your furnace. I'll show you how adjusting your air-fuel ratio to account for the temperature change could save you in fuel consumption. And I'll also go through and show you some techniques for optimizing, getting the most out of the current equipment that you have, and also when would be a good time to look at considering making that step up, either going from ratio regulators or mechanically linked up to an electronically linked system where that would make the most sense. So, Mike, do we have any other questions online?
We do not at the moment.
All right.
AJ, thank you very much for your presentation. If anybody does have any specific application questions, as AJ said, please feel free to either email him or call us at 800-9-LESMAN. You can feel free to ask for AJ. He'll be glad to help you out. As he said, our next webinar is going to be in January, and we'll be on more advanced combustion control and some burner basics. We will be sending out notifications shortly on the date. You can also find it on our website under the Training Center.